We're gonna start doing springs. The mighty springs. No spring cheese? Springs. Um, as was noted earlier, there is like kinetic and potential energy that is associated to springs, but for right now, we're only going to be looking at this through the glasses. True. We're going to be looking at this through the glasses of just forces for now, and then when we start doing work, power, and energy, we'll come back and we'll talk about the kinetic and the potential energy. Unless y'all want to do it all in one go, I'm gonna probably say no on that one, but it makes okay. We can totally do that because in physical science, you have learned that there's good potential energy and there's kinetic energy. So it wouldn't hurt to kind of get an intro to that, and then when we get to the actual energy chapter, you're gonna be like, oh yeah, that's not really that bad. Um, in physical science, it should have been right. Oh, that's true, but you still should have had it. All right. The assumption that we've made so far, the big assumption we've made with forces is that all of the forces are constant. So in the case of a spring, that is actually not the case. So if you're dealing with like something going down a ramp, the force is constant because gravity is constantly pulling it down. So if I make a ramp, this object goes down the ramp at a constant force of mg sine theta. And we can actually say, oh yeah, at any point during the ramp, it's just the force acting on it is going to be the mass times the gravity times the sine of the angle in between them. If you're doing something that's just free falling and you're like falling out of an airplane, your force is constant. And the force that you have is your weight. That's just mg. Everything that we've done so far is under the assumption that our forces are constant. And then we get to these little boogers that are called springs. And this assumption no longer works. We can't do it anymore because if you take an object and you put a spring attached to it, something very interesting happens. When you push this direction, the force will start off pushing back a little bit, but then as you keep going, the force gets stronger. And then as you keep compressing, the force gets stronger. And it's just the nature of the spring itself. Right, because it's a metal. Most springs are made of metal. So as you try to compress and bend that coil inwards, metals springs that are made of metals are a little bit squishy. So what's happening is you're pushing them into place, and you're basically getting a Newton's third law reaction force that's saying, "Hey, we don't really want to go this way. We're going to push you back this way." So the more you push in, the more it resists you. This also works the other way around too. So the more you can move it one direction and the more you move it the other direction. So let's say that we try to, instead of pushing it in or compressing it, we try to stretch the spring. So if we push it in, this is called compression. And if we try to move it out, we're just going to call that stretching. Yeah. What do you want to call it? Tension? We normally only use the word tension with ropes. So is it a tension? Yeah, I think it kind of is. But normally we only use the word tension when we're dealing with ropes. If we pull it this way, then the spring is going to want to pull back, and the more that you stretch it, the stronger the force gets. So if you're out a certain distance, let's say you're out this far, then the force is going to be much greater than if you're only this far away. And this is how springs actually work. Um, and that's how it works. That's how things are going to happen. There is a mathematical model for springs, and it works like this. No, it is not a parabola. Do you want it to? I don't want it to be a parabola. I mean, parabolas kind of scare me, and yeah, that's an algebra thing. I don't know. Nope, no exponential this time. It's actually a straight line. It's a straight line. That's it. Not super bad. Do what? Okay, but it's not constant. Constant would be this, right? Constant would be a flat line across. That means that as you change one of the things, the other thing doesn't change. Okay. it is definitely a linear relationship. So it kind of follows this like y equals mx plus b pattern that we learned in algebra. Totally follows that. The thing is though that at 0, the force is 0. So this plus b we don't even have to worry about. Right. Or in other words, the actual relationship is force is equal to kx. This is what you're going to see, and this is on the formula sheet. This F is equal to kx. And the force is the y-axis value, and the displacement x is in the x value. That kind of makes sense now that I think about it, because it's on the x-axis. But that stands for displacement. Okay. So the k is what we call it is the slope of the line, and that's totally true, and that's actually a really good thing to note. So this slope of this line is equal to k, and I'm just gonna write all these down just to make sure that I've got everything. This is the force of the spring, and it's gonna be equal to the spring constant. Okay, now just like how with friction, friction has values dependent on the surface, the spring constant has values dependent on the spring and the amount it's stretched. So this is the displacement. So a displacement can either be a stretch or a compress. It doesn't matter. Displacement. Can't spell. Did I spell it right? Display. Yeah, I think I did. So this formula is really just like y equals mx. Okay, and we don't really have to worry about the plus b because uh, it's all like it always like the force at 0 should be 0 for a spring is how it should work. Okay. Um, Also, one more fancy word that we probably need to talk about is whenever the spring is uncompressed or unstretched, the position where that is called the equilibrium position. Equilibrium position. Or equilibrium point or whatever you have. Basically, it's the point that this thing is going to move to naturally, okay? And the equilibrium position changes depending on if you take a spring and you have it horizontally located or if you have a spring and you have it vertically located. Because if you have one vertically located, then that spring is going to start to hang down a little bit because gravity's pulling it down. Okay. So, spring constants let's talk about the units for them. Spring constants are measured in newtons per meter. So the force is in newtons, the spring constant is in newtons per meter, and the displacement is measured in meters. So dimensionally, whenever you work through this equation, you're going to end up getting newtons equals newtons. So basically, it's telling you force is equal to force, and that kind of makes sense too. Okay. Right? It's a very easy cancel out situation. The newtons per meters, most of the ones that we have in this classroom are somewhere around like 5 to 10 newtons per meter for spring constants. If you're dealing with like shock absorbers in your car, you've got spring constants of like thousands of newtons per meter. Okay, yeah. I do believe that is correct. The equilibrium position will usually always be perpendicular to the line of action. Yeah, I would agree with that. Because even if we take a spring and we put it on an angle, because there are evil problems like that, and I've seen them, and I'll probably give y'all one later. Right. Okay, that's fair. But that highlights, right? It's a gray highlight. Do you want me to change the highlighter color? I will be inclusive. Hang on. Here we go. Here we go. I can fix this. I can fix this. I Rainbow highlighter? That is one of the most disturbing things I've ever heard in my life. Please. Oh no, the X is oh no. Oh no. Oh no. I don't think there is a rainbow highlighter. We have the options of nothing. There we go. Blue? Blue. Okay. Better? There we go. Yeah. If I get comments, I'm like, why is your shot not yellow? They'll deal with it. It'll be okay. Yeah. They'll be all right. It's okay. All right. Um, So like, yeah, we were talking about how it was perpendicular to the line of action. If you've got like some weird, and I'm just gonna sketch this situation out now, we're not gonna work it yet. If you've got like a mass that's hanging by a spring down here, um, then this would be where your equilibrium position would be, and that would be perpendicular to the line of action because I would consider the line of action on the same way down the ramp and where the spring is because these forces are either going to go this way and this way or this way and this way. Okay. And then that one would be like obviously an mg sine theta, and then this one would be a spring force that's holding it back. So is the equilibrium position perpendicular to the line of action? Yeah, I would probably say so. Yeah. The spring force in this case would be equal to mg sine theta, and that is the easiest way to solve this problem. Yes, exactly. So it looks really difficult, but it's actually not that difficult. Since I've thrown so many incline problems at you guys already, you know that the force going down the plane is mg sine theta. You don't have to derive it anymore unless it specifically says, hey, derive this. Okay, so like if you know that that force going down there is mg sine theta, stick with it. I mean, like that's not a big deal. Um, that's perfectly fine. Now, let's see here. We've got our force, we've got our compression, stretching, spring constant. Y'all already found out that the slope of the line was equal to this. When we do our lab tomorrow, we're gonna find the spring constant of springs by measuring the force and the displacement that happens. So we'll be taking springs and we'll be stretching them out. Do what? The spring constant is always the same if it follows the rules that we have here. Okay, so some springs follow the rules and some springs don't follow the rules. So, like for example, if you have a spring and it does this, whoop, then I would say that that roughly follows the rules. If they do follow the rules, then I'm going to say that these springs are called Hookean. Okay, it kind of, my computer is a potato, so it can't really handle writing and notes and recording at the same time. So every once in a while, it just kind of like blah, 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 spazzes out. So the reason why they call that Hookean is this F equals kx is equal to Hooke's law. Okay, it was named after some old dead guy who came up with this stuff. Um, if it doesn't follow Hooke's law, because there are some springs that don't really follow this law, and usually what ends up happening is it ends up going like, and it kind of like tapers off a little bit. This would be non-Hookean. Okay, and it doesn't follow. Right. So you can't really find your diminishing returns will be a good example of it. Um, Sometimes if you've got really weak slinkies, those really weak slinkies will end up just stretching out rather than actually providing a force. I think I've got a couple of these down here. Uh-oh. There we go. Here's slink. The box is still grabbing me. Um, to an extent, like for example, see how this slinky doesn't really like provide any force like right now. So like it just kind of droops instead. So I would say like on a general note, unless you start really stretching this out. So like for the very beginning displacements and forces, slinkies are in general non-Hookean, I think. But we might actually want to try these on our lab tomorrow to see if it actually does obey Hooke's law or not. Because these don't really provide really big forces, so that means we could actually measure them with our Newton, our spring scales if we wanted to. We wouldn't have to get out the fancy ones. Wouldn't have to get out the fancy ones. Okay. Also springs, you can see like I'm going to hang this one vertically. You can see how it just kind of oscillates back and forth. It moves back to its equilibrium position. And if I could keep my hand still completely, which is like impossible, but if I were to tie this up to something, it would eventually just stop at its equilibrium position, and that would be where it would be just be naturally. That's where it would be by default. Okay? So we would call that the equilibrium position. If you moved it up, it would actually be pushing back at you because it wants to fall back down to its equilibrium position. If you stretch it too far, then that's stretching because it wants to go back up, away, back towards its equilibrium position, like that. Okay? So I know because I'm sitting here and I'm talking about a spring, but I don't actually have a visual for the spring for them. So I'm sorry. I guess I could try to humor them a little bit. um, because I could find some spring animations. Oof. Let's see here. I have yeah, I could just make a short video on it, and I think I can do that too. I don't think there's anything wrong with that. I thought I had a, I guess I closed it. Oh well. I'll make a video of like just a, or we'll do one in the lab tomorrow where we're just like moving a string and a spring and compressing it back and forth. Okay. When it comes to actually doing a Hooke's law calculation or a spring calculation, it's actually pretty easy. It's not nearly as bad as all this like Newton's second law. And the reason why is because the force isn't constant. So there's not a whole lot of stuff we can do to it without getting really complicated in the math. Because if you start dealing with a constantly changing force, that constantly changing force better be constantly changing in a straight line. Okay, so it better be changing linearly because if it changes some other way, that's above our pay grade. So we're not going to mess with that too terribly much. Okay, um, let me give you all a couple of easy scenarios. Easy scenario number one: if you have a spring that is hanging from the ceiling. And I used to, before I got the new room, I used to actually hang masses from the ceiling. And I can't do that anymore. I'll get in trouble. But we'll find some way to hang some masses because we need to. And we've got a mass that's hanging like this. Let's say that this mass in here is 5 kilograms. And whenever we hook this mass up to the spring, it stretches down and it ends up stretching down a total distance of 45 centimeters. And I'm going to use centimeters because it's easier to measure centimeters than it is to measure meters. But we need to make sure that whenever we have them done, we need to make sure that our measurements, whenever we finish it, are in meters for our calculations. Because the displacement should be in meters for the newtons to end up to cancel out dimensionally. We need it to be dimensionally correct. And if we've got the weight and the distance, I think we can find the spring constant. So I'm going to say, what is the spring constant? Spring constant. Question mark. All right, so free body diagram time. The spring, the mass, everything there becomes a point. How many forces do I have acting on that? Just two? What and what? Okay, so we got gravity going down, and we got a spring force going up. What do y'all want to call the spring force? FS? I'm fine with that. Okay. FS means force of spring. Okay, not force of summer, not force of sausage, force of spring, right? I'm fine with that. I can't think of any other ones that would start with the letter S except for maybe static friction. But you would use the mu sub S in that case. So there's a difference. All right. So if there's no other forces, I think the next thing that we need to ask is it moving? Okay. Is it accelerating? Okay. I guess I should have asked, is it accelerating first then? So that means there's no acceleration. So what does that mean? The forces are balanced, but you know that's how I'm not going to say it. I'm going to say that the sum of the forces in the y direction is equal to 0. Good. Yeah, the sum of the forces in the y direction is equal to 0, so that means that these are balanced forces. So we can go ahead and skip the adding them together, and we can say that the force of the spring is equal to the force of gravity, and I'm fine with that. That's okay. Now, what is the force of the spring? Well, that's the force of gravity. Yeah, yeah, the force of gravity is 50 newtons. But they were equal. Yeah, they are going to be equal, but saying 50 equals 50 is not going to be helpful, right? We are looking for the spring constant. There you go. Yeah. So we're going to use the expression for the force of a spring, and we're going to say that's equal to kx. The force of the spring is kx, and the force of gravity is 50. We know that this is 0.45 meters. We've got to switch it over. So that's going to be 0.45. So we're going to divide both sides. So So K is going to be equal to 50 divided by 0.45 meters. 111. 111 newtons? Okay. So we've got a spring constant of 111 newtons per meter, because that's 50 newtons divided by 0.45 meters. So our spring constant is measured in Newton meters, and the spring constant should always be measured in Newton meters. Okay. Pounds per foot, yeah, or pounds per inch, depending on what you would have. Okay. But we are metric in physics. We are super metric mode boys. Okay. Um, Pretty easy, not too bad, right? Can I make it more complicated? I should not. Yeah, it'll definitely help y'all in the homework. So, um, well, I mean that's okay. I mean I can always give y'all more homework. I've got to honestly, everybody, the Book of Evil. There is a large amount of homework that I haven't given y'all yet, and I need to. I've been being nice, but I need to stop being nice. Yeah, yeah. Um, I'm not meaning to like. I'm not gonna throw. I'm not gonna throw too many things from the Book of Evil at you guys because, well, I like you guys. I don't wanna hurt you too badly yet. I think we need to wait until rotational motion before like destruction mode occurs. Um, Actually, it looks like they. Huh. Okay. That chapter didn't have any spring problems in it, so I may have to make one up. Huh. How about that? Oh no, I'm gonna make one up. It's happening. I'm gonna make it up. Creative mode time. I already showed you guys the spring and the on the yeah, on the dangly box. So I don't know. Okay, let's do it this way. Let's make our life a little bit more complicated. Where's the spring? No. No, it's gonna be at the bottom of the ramp. What? Ready for this? Big brain time. Here we go. We're gonna put our mass right here, and we're gonna put a pulley right here, and we're gonna put a what? And we're gonna put a big mass right here. Let's make this. This is kind of like an additive machine. This is gonna be 10 kilograms right here, and on the other side, there's gonna be. This is attached to a spring. Oh, this is sadistic. Um, let's see here. Let's say that we got a 5 kilogram mass right here. I want. I'm going to become caveman. So, right? I'm going to ask us. I'm going to say, what is the spring constant? What is the spring constant? And I think, honestly, once we get the angle, let's say that this is 20 degrees. I think that's all we need. Let's find out if I'm right or not. I don't really. I could be wrong. If I'm wrong, we'll add some more information. But I think that's all we need. We've got a 10 kilogram mass that's pulling it. Obviously, if there's no friction involved, then the 10 kilogram mass is going to win. Let's also make an assumption that this thing is going to, once it reaches a certain, once it reaches a certain stretch point, that it's not going to move anymore. Okay, so we're going to assume that it doesn't move anymore. Do what? I think I think in order to actually find the spring constant, now that I mentioned that because I said it's not moving anymore, I think we will need one more piece of information. I think we're going to need how far it stretches. So I think we're going to need how far it stretches before it actually does its thing. So let's say that whenever it gets pulled, that it stretches out 20 centimeters, which is a pretty big stretch for a spring. We'll see what happens. 10 kilogram mass is like 22, 23 pounds, so we'll see. Okay. So, what would y'all do? You have a complicated situation that is not normal. Okay, that's a good idea. What are we free bodying? Free body diagram? Okay, we're gonna do the 5 kilogram mass. I think that's a good idea. So the 5 kilogram mass and the spring attached to it, and the other weight attached to it that's pulling it, and the string and the ramp becomes a dot. Perfect. Okay, that is true physics style right there. Now, what forces do we have acting on this object? Okay, so I know we've got gravity, so that's going to be going down this way, right? Normal is going to be going the perpendicular to the line of action. So I'm going to write N for normal. I'm going to write mg for gravity. Oh, what else do we have? We have a spring force. What direction is the spring force going? It is going left this way. When it's stretching out this way. So let's assume that the equilibrium position, I'm going to put it in red. Let's assume that it's right here. Okay, so it's being stretched. So which way is the spring going to want to go? Is it going to want to push or pull? It's going to want to pull, so it's going to want to go to the right. Yeah. Okay. And then what about what about this guy? What about this guy? Well, no, well, that is tension. Yeah. So like it's pulling. So I'm going to call this rope tension. I'm going to put T going this way. Yay, four forces. It's not. Not this time. It's not this time. The spring force is a part of the solution, but it is not 100% equal to the solution because there are two things wanting it to go down the hill, and there is one thing wanting it to go up the hill. So therefore, we can't say that it's just the spring force alone. We have to include the force of gravity as well, but not just the force of gravity, a component to the force of gravity. Okay? So, first of all, I'm going to go ahead and draw the line of action. Would you describe the line of action to me? There you go. Yeah, yeah. Parallel to the ramp, and then once we get to the pulley, around the pulley. So I'm going to go boop, 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 and I'm going to go this way. So when I draw my arrows need to go along that line of action, which means on the free body diagram, my line of action goes like this. So tension and the force of the spring, they're good. MG, MG is no bueno. MG needs to be broken up because if we kind of make our crosshairs like this, 90 degrees, then MG is not in line with either one of those, which means we need to make it in line with those. So we've got to break it down into components. Okay. There we go. What? Y'all already know that you told me the components earlier. Sine theta is going which way? Vertical? I don't know what vertical means. Like I'm looking at something that's like cattywampus lopsided. Sine goes perpendicular line of action. You're crazy. The angle is right here. So this is going to be, yeah, it's still going to be 20. Yeah, it's still going to be 20. So the right, so like here's gravity down this way. So the similar triangle that gets made, notice how the right triangle is kind of flipped over. So like over here, the right angle is on this side, but over here, the 20 is on top. So it kind of gets like flipped over. But it is there. So this means this top one, the perpendicular one is mg cosine theta, and the one on the bottom is mg sine theta. You have mg cosine theta and mg sine theta. And y'all told me that earlier. You said if it's going down the ramp, then it's going to be mg sine theta. That doesn't change. It does not change. Okay, so anytime you're going down a ramp, it is mg sine theta. There are no exceptions that I can think of constantly at this time. Unless you got super big brain on me. And if you said something, I might be able to sway my opinion. But I'm going to say right now that if you got the angle in the bottom right, it's mg sine theta. Just flat out. Okay? Now what? That's not what I'm going to do next. I'm going to do is it moving? Okay. So, no. Are the forces balanced? Okay, so the sum of the forces in the x direction is what? 0. And the sum of the forces in the y direction is 0. Okay? Some of these will be helpful to us, some of these won't be helpful to us. I think the x direction is the way that we want to go, which is the way that's going up and down the ramp. Okay, so now we can talk about the forces that we were doing earlier. Okay, now we can talk about the forces. So which way is positive, which way is negative? Right now. Okay, so positive, positive, negative, negative, right? We all agree? Okay, don't switch that on me. If we're all gonna agree on that, don't switch it on me. You're gonna drive me crazy. This is already a crazy enough subject as it is. I don't need to go even more crazy. So let's add these up. How many forces do I have in the x direction? 3. 3. Yeah, there's this guy, bloop, this guy, bloop, and this guy, bloop. Okay, mg sine theta is in the x direction. So you're right. There are two forces, but there is also a component of a third force. I guess if we wanted to get like super technical about it, there are two forces and a component of a third force. So here we go. We're gonna do this. We've got mg sine theta. That's positive. So mg sine theta plus the force of the spring minus tension equals 0. We can change a couple of these things around. Mg sine theta. Okay, we can do that, yeah. Mg sine theta plus the force of the spring, that's true, is equal to the tension. We can just add the tension to both sides. We know that the tension is equal to something. What's pulling? Okay, so the 10 kilogram block is providing the tension, correct? What is the force of the 10 kilogram block? 10 times 10, right? mg. So the mass is 10, the acceleration due to gravity is 10, so that would be 10 times 10, which is 100. So let's just go ahead, and I'm going to erase this t, and I'm going to write 100 newtons in. So 100 newtons. It's lazier for me to write it that way than to rewrite the entire expression. Mg sine theta is actually a number as well too, because we know the mass, we know the gravity, we know sine theta. What'd y'all get? 17 newtons? 17.1? Is everybody okay with 17.1? Okay, so we're going to do 17.1 newtons. Okay. The force of the spring, we can call it Kx. K20? No. K.2. Right? You gotta make sure that you change it over to from centimeters to meters, because the displacement is in meters. Otherwise, you're going to end up with a way smaller force than what you thought you were going to get. Okay, and I think it's algebra from here. So we're going to subtract 17.1. We're going to divide by 0.2, and that means our spring constant is going to come out to be whatever the heck that is. 414. Do I get a second? Just a second, yeah. Okay, newtons per meter. Y'all double check that real quick and make sure that the numbers actually do work out. It seems reasonable to get 414.5 newtons per meter for this spring constant. And that's not too bad for just making something up off the top of your head. It's a reasonable number, 414. It would be a pretty stiff spring, but then again, you're literally taking like 23 pounds and dropping it like dead weight. So yeah, I mean, you're going to need a pretty stiff spring to be able to do that. Okay. I think that wasn't too bad, right? Right. Like once you get one, and that's why if y'all haven't noticed yet, I always draw a picture to every problem that we do. Even if it's a simple problem, I'll still usually draw a picture, and that's because it helps me get an idea of like what to add together and what to subtract and where everything goes in place. I would recommend for you guys to always draw a picture as well. Even if you think that I don't need a picture, that probably is an indication that you need to draw a picture. Okay. And I've, in regular physics classes, I'll have people be like, "Well, I'm not very good at drawing." Be like, "I don't really care. It doesn't matter. It can look like a big pile of crap. I just need to know what direction the arrows are going. That's the important part." So, yeah, back whenever I was doing regular physics, I kind of miss it a little bit. All right. So, do you want to try another one of those, or all right? I'm gonna see if I can try to find one, but I'm gonna have to find the force chapter. Let's see here. Applying Newton's laws. Spring. Springs. Um, Forces. 105. We're gonna try this. 105. 105. Tension force. Friction. Oh, oh, oh. Um, no, that didn't. Ugh. This book doesn't really have any good ones in it, to be honest. That's kind of scary. Hmm. Let me try the other Book of Evil. Book of Evil round 2. Yeah, no, this one is the granddaddy, but it's not it's the granddaddy Book of Evil. This is the one that I took in college, so. Oh, it's heavier. I don't know if it's more wisdom, but it's definitely heavier. I do. I have lots of spell books in terms of like things that make no sense. Uh, let's see. Uh, oh, come on. Be nice to me. Aha. Okay. Yeah, that one we might not be able to. I'm going to be doing this recording and you're going to hear people just like randomly spouting G codes. It's going to be like, what? That doesn't even make any sense. Okay, that one's just evil. I don't necessarily think we need to do that one. I don't know. You're right. You're right. That's true. But, see, did mass slides down. Okay, we can try this one. We can try this one. Now I got to find my pen. Okay. Kind of does, doesn't it? Oops. Draw it this way. We are going to end up compressing it. Yeah. So there's a spring that's just sitting there, and there's a mass on top of it. And this mass is a 3 kilogram mass. And we're just going to like drop this thing down the slide. And the spring constant down below has a spring constant of, I think it said 400 newtons per meter, which is not too different from what we had just had. 400 newtons per meter. And the angle of the incline is 30 degrees. 30 degrees. And I think it gives us one more piece of information. I think. Let's see here. A mass starts from rest and slides a distance d down a frictionless incline. While sliding, it contacts the unstressed spring of negligible mass, as shown in figure that right there. There's the picture. The mass slides an additional distance x as it is brought momentarily to rest by compression of the spring of force constant k. Find the initial separation d between the mass and the spring. Okay. Yeah, so like no, what it wants us to find is it actually wants us to find the initial distance here. Okay. Okay, so like I'll go ahead and I'll tell y'all this. The only way that we're going to be able to solve this to find out how far the only way we're going to be able to solve this is it was we don't have any information about the acceleration of the object, right? So the only way we're going to be able to solve this is to think about it from a different viewpoint. We're going to have to think about it in terms of energy in order to be able to solve for it. Okay? So maybe I want to kind of give you guys a couple of ideas on what it means to actually store energy inside of a spring. So, y'all know about kinetic? No? Is it too much? We can we can come back to it. We can come back to it later. We'll write Wait a minute. Wait. Wait, people are hiding under desks, so I think we might I think we might need to Biggie Cheese this one and just come back to it. So yeah, every time I search Biggie Cheese in my notes, it's going to show things that we haven't done yet that we need to go back to. Oh God, we only have 4 minutes. That's not a lot of time. I forgot that it's on advisory schedule. Dadgummit. Okay, so tell you what then. Well, I mean, like like think about it, guys. If you're dealing with this in terms of forces, if you're looking at it from a dynamic standpoint, you've got mg sine of theta going down, but you don't have anything dealing with the kinematic equations. So using a force standpoint for this problem is not practical. We would actually have to solve this one from an energy standpoint and not a force standpoint, because it's asking about that distance and not a compression distance. So we can't use F equals kx. Okay, so yeah, we're gonna Biggie cheese this one, and we'll whenever we get to back to energy, we will come back to it. So yeah, I literally had people crying under desk on that one. So apparently we'll come back to it in due time. In due time.